You did everything right. You noticed a slow query, you added an index to fix it, and the database completely ignored it. Instead of taking the fast lane you built, it swerves right back into traffic and checks every single row one by one. It feels like a bug, but your database is actually doing this on purpose. The tool that makes this decision, the query planner, isn't guessing. It acts like an incredibly strict accountant. Before it runs your query, it calculates the literal, physical cost of jumping around your hard drive versus reading straight through the data. This chart shows how that accountant makes the decision. The most important number on the bottom axis is called selectivity. That is simply the percentage of total rows your query is asking for. Are you looking for one specific user or half of your entire customer base? If the database decides to read the entire table from top to bottom, what we call a sequential scan, the cost is pretty much fixed. You pay one flat rate to read all the data in order, whether your query needs 5% of the rows or 50%. Using an index is entirely different. An index forces the database to make a separate physical jump on the hard drive for every single matching row. If you only need a few rows, it's incredibly cheap. But as you ask for more data, those individual jumps add up quickly, and the cost rockets upward. Notice where those two lines cross. That glowing dot is the exact moment an index becomes more expensive than reading the whole table. If your query asks for enough data to push you past that point, the database throws away the index because a full table scan is physically cheaper. To figure out where you land on that graph, the planner has to predict how many rows your query will return before it actually runs it. To do that, it checks a hidden set of statistics, acting as a cheat sheet. This diagram shows exactly how the database makes its guess. First, it checks a list of its most popular data, things like a status column where almost everyone is labeled active. If your query asks for one of these common values, the database already knows the exact percentage of rows that will match. If you're looking for something less common, the database moves to its backup plan. It uses a histogram, which groups your data into equal-sized buckets. It finds the bucket your value belongs to, looks at the size of that bucket, and creates a highly accurate, educated guess. Once the planner has that estimated percentage, it plugs it straight into this mathematical formula to calculate the final physical cost of using your index. The most crucial part of this equation is that first variable. It represents the penalty the database charges for making erratic, random jumps around your hard drive. Out of the box, that penalty is given a weight of 4. But there is a catch. If you recently imported millions of rows and the database hasn't updated its cheat sheet yet, those bucket estimates will be completely wrong. The formula breaks down, and the database makes terrible decisions, choosing full table scans when it shouldn't. Even with perfect statistics, there is a physical reality that can completely ruin your index performance. It's called correlation. This graphic shows two different ways data physically sits on your drive. On the left, the data is perfectly sorted, like dates that were added in chronological order. When the index asks for a range of dates, the hard drive smoothly reads down the list in one clean sweep. But on the right, the data is totally randomized, like a list of random user IDs. Now, the index forces the hard drive to bounce wildly back and forth to collect the pieces. It takes significantly more time and energy to gather the exact same number of rows. When the database realizes your data is chaotic, but you still need a decent chunk of rows, it doesn't give up and scan the entire table. It has a clever compromise. It runs a bitmap index scan. First, it quickly scans the index to figure out exactly which blocks of the hard drive hold your data. It builds a master map of those locations, and then it visits them sequentially, reading each required block exactly once with zero backtracking. The database optimizer is incredibly flexible. It constantly adjusts its approach to match the physical chaos of how your data is actually stored. To see exactly which strategy the planner picked and why, you can ask it for a receipt. By putting the words explain, analyze in front of your query, you force the database to show its math. When you look at that receipt, pay close attention to the row counts. If the database estimated it would find 1 row, but actually hit 5 million, its internal cheat sheet is out of date. Updating those statistics usually fixes the problem instantly. But what if the math is right? The index is there, and it still ignores it. Remember that jump penalty we looked at earlier, the one set to 4? That number was chosen in 1996. It was designed for mechanical, spinning hard drives,
where physically moving a metal arm to a new location was a huge bottleneck. Today, your database almost certainly runs on a solid-state drive. SSDs don't have moving parts. Jumping around is virtually instant. That means the database is heavily penalizing indexes for a mechanical delay that no longer exists. When we update that penalty to reflect modern hardware, the cost curve completely changes. The index scan becomes incredibly cheap, and the crossover point slides way out. Suddenly, the database starts choosing the index for almost every query. You can fix this on your system with a single line of configuration. Running this command tells the planner it's sitting on an SSD. It requires zero downtime, and it takes effect immediately. So the next time your database ignores an index, don't panic. You don't necessarily need to redesign your tables or write complex queries. You just need to make sure the planner has accurate statistics and that it knows what century its hardware is from.